the newly hired faculty, still shiny. And today we have Cris Panda, our new assistant professor in the optical sciences. And let me introduce Cris a little bit. So he graduated from Reed College and then went to Harvard for his AM degree and PhD degrees. And in Harvard, he studied how to measure the electric dipole moment very, very accurately. I always calculated, not measured, but he's the person who actually measured the electric dipole. So, and then he joined the UC Berkeley as a postdoc. And then in UC Berkeley, he studied the lattice atom interferometer. And remarkably, the coherence time he achieved is more than 1 minute. So let's welcome the speaker.
Thank you for that really nice introduction. It's really my pleasure to be here. For the first time as a professor, I was here last year giving a similar talk as a candidate, so it's really good to be here. So what I want to tell you today, it's about this new direction in quantum sensing and quantum metrology, in which we're taking a spin on typical atom interferometry. Instead of letting the atoms fall, we catch them in an optical lattice. And this technique now allows us to measure this atomic spatial superposition states with measurement time and coherence that are much beyond what was possible before. That's now at the minute scale. This is a diagram of the experiment that we did last year, in which we use this spatial superposition state. So you see these atoms, they're now in 2 wave packets. Each wave packet is in a different lattice site. And we hold them next to a tungsten source mass. And we can measure the gravity from this tungsten source mass with precision that's much better than what was previously possible. So let me just start with some motivation. A lot of our reasons for doing this are from fundamental physics. And we have strong evidence from astrophysical observations that the universe is dark. So most of the matter and energy in our universe is dark energy or dark matter. And really only a very small fraction, about 4%, is matter that we can study here on Earth at facilities such as the Large Hadron Collider. So all of this other stuff we know is out there because of inertial or gravitational signals. We can measure rotation curves of galaxies and the accelerating expansion of the universe. But we have no idea what their macroscopic composition is, right? Another problem in cosmology and fundamental physics is also about the 4 fundamental forces. 3 of them, electromagnetic, weak, and strong, are really well described by quantum field theories. They tend to be quite strong at small scale. And the other one, gravity, is much weaker, 30, 40 orders of magnitude weaker than the other ones, and is described quite well by general relativity. Now at low energy, you can write theories of gravity that sort of makes sense, but as you go to high energy, sort of free for all, and really no one knows how this could work out. So in order to study problems like this, you might build systems which study each one of these arms very precisely, but our approach is to build systems which are quantum in nature, using atoms, and are quite sensitive to gravity. So it's using systems that are sensitive to both type of theories that you're trying to look at. So why use atomic and molecular quantum sensors? That's a good question. I have this statement here: at quantum level, all atoms and molecules are the same. So that sounds very nice, right? I have a system that I can describe really well, use math to write a very precise equation of my system, and that's a very precise measurement device, maybe. In reality, in experiments, it's much more challenging, right? If I take atoms and molecules in the air around us, 300 Kelvin, they're moving fast at hundreds of meters per second. That only gives me microseconds of measurement time in my experiment. What's even more, the number of quantum states that I have populated at room temperature is very high, right? I'm looking at tens of quantum states for the simplest atoms, goes up to hundreds of thousands for more complicated atoms. Molecules, you're looking at tens of thousands, and things like proteins or more complex systems, millions and so on. So it's very, very challenging. And I think this is a lot of the challenge in this field of atomic physics, is taking control of that complexity and using it to your advantage. And this is the methods that we have used to do that over the last decades, literally 100 years now, or even more, is to use interactions of these atoms and molecules with coherent radiation. So lasers that are very stable. And this has allowed us to build a toolbox for precise quantum control of these objects of atoms or molecules at the single quantum state. And this is what I'm trying to show here. Over the years, in order to gain more quantum control, we tend to give away complexity. So use simpler systems, maybe use a single atom instead of a large ensemble. But that was the trade-off so far. And now people talk about this thing, the second quantum revolution. A lot of people mean quantum computing, quantum information. The way I think about it is for atomic physics is actually this ability now of having quantum control of your system at a single level. So extremely precise levels of control and going beyond that. So now we can start with a small number of atoms, each in a precisely known quantum state, and build our systems of billions of atoms from the ground up. So you end up with a system that's extremely well described by your math and can be very well used for precision measurement. So this is what's shown here. Instead of just using one atom, or maybe even an atom interacting with an optical lattice, now you can use more complex systems. And the complexity goes up, but in a different way than before. Now it goes up in a controlled way in which each single element in your system is well understood and acts as an ensemble. So another idea here is to use specific properties of quantum mechanics, superposition, entanglement, and we can use those to increase sensitivity and accuracy and also reduce systematic effects. So can we amplify and isolate the effects that we want in our systems and take out the effects that we don't, noise? So there are two main goals, I think, to this research. One of them is to build extremely precise state-of-the-art experiments in the laboratory. And we can use those to study fundamental physics. The other direction is to find ways to bring these quantum systems into the real world. So find industrial and commercial applications for this type of devices. And to convince you even better that this is a good approach, I can give you a few examples of different quantum sensors that have been used over the years for both of these goals. So quantum systems are quite versatile, and the single atom can have many different roles depending on what quantum state you use for the sensing procedure. And I just separate them kind of arbitrarily into three categories: magnetometers, clocks, and atom interferometers. Magnetometers typically use quantum states that are sensitive to fields, maybe to magnetic fields, electric fields, temperature, and so on. So it's a bit of a misnomer. It's really much more general than just magnetic fields, and have been used for many different fundamental physics applications there. So dark matter, Lorentz violation searches, they measured parity violation in atoms. And the topic that, as Daniel was saying at the beginning, was the topic of my PhD, was this measurement of the electric dipole moment of the electron. And this is a very important measurement. Why is that? So if we look at the electron, we know it has a spin. So that comes with a magnetic moment, right? Now, if the electron also had an electric dipole moment, that must be aligned with the spin of this electron. So if I perform a time reversal operation, I end up with this other electron, in which the spin is pointing in the other direction, while the electric dipole moment is up. So intrinsically, this quantity is violating of this fundamental symmetry in nature, T symmetry. Why does that matter? It's because it's one of the ingredients that would be required to explain why our universe is made out of matter and not antimatter. So antimatter is this type of particles that correspond to regular matter particles. They just have its opposite charge, and it turns out the universe is made out of matter. Why is that? We don't know. And this is the type of physics that we have to look for. So to tell you a bit more about that, we use a molecule, the thorium monoxide molecule, to do this measurement. And the goal is to measure the small energy shift, which is proportional to the electric dipole moment dE times an electric field. So if you want to measure a large signal from the electric dipole moment, you want the largest electric field possible. And this is where the molecule, with all its complexity and all of the additional levels and all of the lasers that you have to use to control it, it really gives you a huge advantage in this respect. So this electric field that's accessible in the molecule is 78 gigavolts per centimeter. those who worked in an experiment, you know that that's 1,000 times larger than you might be able to get in an atoms and about 1,000,000 times larger than in a lab. So it's really a huge enhancement to the signal of interest. And this is shown with the results that were able to come out of that kind of measurements. So this is a plot that shows the different theories that are being tested. This is the value of the electric dipole moment. It goes from 10 to the minus 25 to 10 to the minus 39, so a bunch of orders of magnitude. The standard model predicts that the electric dipole moment is very, very small, so we're not going to be there. But there's a lot of theories of physics beyond the standard model, particularly supersymmetry, but also more generic models that in general predict large values of this electric dipole. So doing more precise measurements allow us to cut into the parameter space available to these theories. So now we can extend with the ACME1 result. This is the result that occurred as I was studying at Harvard in my first couple of years there. We were able to really exclude a lot of this various models of physics beyond the standard model. And then with ACME2, we were able to go even beyond that with another order of magnitude. And the progress keeps going. ACME3 is projected to do even better than that. So this is really a great example how experiments at the small scale that can happen in a laboratory can put bounds on particle physics and on theories of physics beyond the standard model with precision that matches, I think, the large colliders, right? So that's all great. What about clocks, right? So clocks, I think, are the best example of atomic physics coming out into the real world. And it's been used for fundamental physics in test of variation of fundamental constants, gravitation, measuring the gravitational redshift. So now they can see the clocks ticking at different rates over a distance of a few millimeters. So really, this is an atomic cloud of a millimeter size. And they can see the clock up here is ticking at a different rate than the clock down here because of the gravitational redshift of the Earth. So that's the amazing precision. These are available in small packages now commercially and have been so for a long time. And this technology is extremely important for GPS and navigation and so on. And this is really an amazing plot that shows the progress of clock technology, of atomic clocks over the last half a decade or even more than that. And people call this the Moore law of atomic physics because the progress is just so amazing. So even since the 50s, the clock technology has been increasing in clock fractional uncertainty as a function of time at an amazing rate of more than an order of magnitude per decade. And you can see different technologies coming around. So first they use microwave beams, then they move to fountains. And what's even more amazing, over the last couple of decades, the rate of progress has been increasing even more than that. And that's because of mostly two new technologies that have been implemented. So one of them is using optical transitions. And then the second one is using trapped atoms and ions. So they use optical lattices to trap neutral atoms and then ion traps to really measure this atomic systems with extremely long coherence time. And this is, I think, one of the inspirations for the research that I'll be telling you about today, in which we use very similar techniques, not trapping a clock state, but trapping an atom interferometer state, so spatial superposition state. So if in clocks they measure time, our goal is instead to measure space. So we're measuring accelerations, we're measuring gravity. And the idea is, instead of letting your system free fall and being limited in the coherence of your experiment by that, you are holding it in an optical lattice for 70 seconds. So this is the outline of my talk. So I'll start with a little bit of a review of atom interferometry. Then I'll tell you about this new method, the optical lattice interferometer. I'll tell you about some of the theory behind it and then also experiment. I'll talk about this experiment that we did, in which we measured the gravity from a small tungsten source mass with state-of-the-art precision, really the best measurement, and how that probes Phi forces, places bounds on dark energy. And then I'll tell you about some of the work that we do here at Arizona and kind of future directions and ideas. So I'll take a little break and see if there's any questions at this point. It was a long introduction. Are there any questions? Right, question right there. What was it?
What's the fifth force?
So there's these four forces I showed you: electromagnetic, weak, strong, and gravity. The question is there a fifth one, right? We don't know why there's only four. And a lot of these problems in cosmology require a fifth force to kind of explain them. For example, this accelerating universe that's attributed to dark energy might be explained by a fifth force that's causing that kind of expansion. So that's the sort of theories that we could be testing by looking at the gravity from the small objects, and specifically deviations from the expected gravity from Newtonian theory. It's a good question. Right, any more questions at this point?
Yeah, maybe in the plot that you showed about the theories, I thought that the standard model expects a zero dipole moment for the electric dipole moment for the electron, but it shows a small but positive.
That's right. Yeah. So there is a non-zero dipole moment, and that's a very good expert level question. So I'm happy. Let me go back to the plot. Where was that? Here. So actually, this is kind of outdated. This is now has moved up to 10 to the minus 37 on 10 to the minus 36. So the reason that comes in, we do have CP violation in these particles called kaons. So they're mesons, they're heavy baryonic particles. Now we're measuring the electric dipole moment of electron. The electron is a lepton. So the way that these particles contribute to an electric dipole moment for the electron is at fourth order loop diagrams. So it's a very small correction, but it's there and can be calculated. And actually, it's a bit higher now than it was thought.
The coupling with the other fields, but
Exactly.
The standard model gives a zero. Dipole moment for the electron, right? But when you couple it to the
So in QED is zero,
Yeah.
but then when you include the hadronic corrections, yeah, it's not. Then it's non-zero. Yeah, I mean, I think there's reasons to believe it will be non-zero in this theories of beyond standard model physics. Yeah, but in the standard model, yeah, that there has been no measurement of a leptonic CP violation parameter so far. Yeah, that's right. Good. Okay, I guess in the interest of time, I'll keep going. But feel free to interrupt with more questions. So I want to tell you about atom interferometry. How does that work, right? We're in the College of Optics, so we've all seen laser interferometry. Of course, this is the bread and butter of us here. Okay, how does it work? It's pretty simple, right? You take a laser, a light source, and then you send it onto a beam splitter that splits it into two different paths. There's some mirrors at the end of each path that sends the beam back onto each other. Then it gets recombined, and then you detect the interference signal on a photodetector. Now, this is not just a regular interferometer, right? We all know this one is LIGO, very famous interferometer. And the power of this device, of course, comes from the fact that the wavelength of the light is really small. So it's about 1 micron or so. But the length of each arm is very long. So it's 4 kilometers, but there's these filled up cavities that really make it effectively 200 kilometers or so. So that's already a factor of a part in a billion times enhancement on the signal of interest. And these interferometers have been extremely sensitive, right? So LIGO is able to measure strains or differences in the two paths at the level of, I think, a part in 10 to the 22 or even better now. And that's really amazing precision that's sufficient to measure this catastrophic, intense intergalactic kind of events in which you have black holes that are a few tens of mass of the sun that collide, and then in a fraction of a second, they emit more gravitational energy than the entire universe electromagnetic energy combined, right? So it's just amazing that you can measure these signals happen at hundreds of billions of years away. And these devices are so sensitive that they can measure them after all of that propagation down to the Earth, right? So, okay, laser interferometers are obviously great. What about atom interferometers? Well, the idea is similar, but the roles are a bit reversed. So first of all, we know that atoms are also waves. Louis de Broglie taught us that about 100 years ago. So we can use that property of matter to create an interferometer. So I take an atom, I use a laser beam to perform a pi-half beam splitter pulse that sends the atoms onto 2 different wave packets that can propagate along different paths, such as shown here. In the middle, I use a pi pulse. It kind of looks like a mirror pulse that sends the 2 arms back towards each other. They recombine at the end, and then we measure, use the pi half pulse to measure interference. So it's very similar to light interferometer, there's two interferometer port outputs, S1 and S2. I can calculate this property called the asymmetry, which is just the difference between the two divided by the sum. And it turns out that this asymmetry is proportional to the contrast. That's just the amplitude of the measured wave times the sine of the delta phi, so the phase of the interferometer. And this is a nice fringe that you can see, and it looks like a very nice Gaussian wave or sinusoidal wave. And you scan some parameters to vary the phase, and you see these variations, these changes in the asymmetry. Okay, so where does the atom interferometer phase come from? There's a lot of sources, but the two main ones are sort of easy to understand. So there's the propagation phase. This is what Feynman taught us, and Kraut-Kohn and Tanucci. So these guys told us how to do this. It's pretty straightforward. So all I have to do is to take this interferometer, I calculate the classical trajectory of each path, and then I integrate the Lagrangian of my system over that classical trajectory. So I do that for each path, and then I take the difference, and that gives me the propagation phase. There's also another phase that comes from the fact that the atoms interact with the lasers at these different points in time. So initially, for the mirror pulse in the middle at time t, and then the recombination pulse at time 2t. And basically, the laser phase gets imprinted onto the phase of the atom. So it's basically this k, this wave number times the z, the position of the atom or of the wave packet of the specific arm at that point in time when the pulse was sent out. I'll just mention that this is a height versus time plot. So the atom is moving vertically along the axis of gravity, and we're plotting that vertical position as a function of time. So we're not drawing the atoms horizontally. I get that question a lot, and it can be quite confusing. But if you take this phase sources into account and then calculate the total phase of this type of interferometer, a Mach-Zehnder interferometer, you end up with a pretty nice simple formula. It's k, the wave number, times g, the gravitational acceleration in your local field, times t squared. So t is the time between these pulses. And because this parameter can be quite large, so t is an important parameter, you want the time to be as long as possible. It's possible to get a very large phase for this interferometer. So something like 10 to the 9 radians of phase is possible. And now if that fringe is stable and I can measure it to some precision of maybe a milliradian or even better than that, that gives me a very, very good sensitive measurement device. And I can use that to extract G, for example, or K. Depends what parameter I'm interested in. Okay, so what can you do with these devices? What can you do with atom interferometers? Well, you can bring them out and do inertial sensing. So you can build them in compact setups. This is a setup that was built at UC Berkeley in an academic lab. It's kind of the size of a little cart here. It can be put in a U-Haul truck, and then they drove it in the Berkeley Hills up here, and they stopped at different locations, measured the local gravity, and it matches sort of the expected prediction from the gradient of the Earth, right? As you go up, the gravity gets weaker. So there's a lot of interest in building these devices into portable, compact, robust platforms that can be brought out into the world and used for measurements. There's a lot of companies doing that. The government is interested in that, so that's very cool. Also, atom interferometer has been extremely successful in fundamental measurements in precision interferometry. And there's a few measurements listed here. I'll talk a bit more about two of them, the gravitational constant big G. So this is a measurement done with big source masses, hundreds of kilograms. And then they have two atom interferometers. One is below the source mass, one is above. And then they measure the difference in the gravitational field, and then they can extract the attraction from the source masses. Now, the gravitational constant has a really funny history. It's probably the first constant to be precisely measured. That was done more than 300 years ago by this guy Cavendish. So he has this torsion balance, and he was very precise, back then. I mean, he was able to extract this constant to a precision of 1 in 100, or even a bit better than that. Now, 3 centuries later, and hundreds of measurements later, all done with classical sensors, a lot of money spent. We know this constant to a bit better than an order of magnitude more. So we know it to like a part in 10 to the 4 or so. Sometimes the precision actually goes down because they do more measurements and actually they don't agree. and there's a lot of systematic errors. So this is a very challenging measurement and very hard to pinpoint. And I think a lot of the methods use classical devices that have a lot of common mode systematics. The idea was, can we use a quantum sensor instead? And can that allow us to eliminate some of the systematics and get better precision? The second type of measurement I want to talk to you about is the fifth force, searching for fifth forces. This is a type of measurement that I'll talk more in detail a bit later, but the idea is that we know that the universe is expanding at an accelerated rate. There's this thing called dark energy that we attribute it to. We know that this force is very strong in intergalactic space, but we don't see it here on Earth. So one explanation for that is screen potentials. Maybe the strength of this force depends on the local matter energy density. So here on Earth is very weak because there's a lot of matter. There's air around us, but in intergalactic space is very strong. So these theories are called chameleons, symmetrons, and so on. And probing them has been an interesting kind of application. And using atoms in a dilute sample to measure the gravity of a small tungsten source mass, it's really one of the best approaches to do that. So this is the exclusion plot of some of these theories. It shows the strength of this interaction as a function of the mass of this new particle. And then it shows that atom interferometry is really now beyond Newton interferometry and cutting a very wide parameter space into this plot, and sort of also augmented by classical sensors, but those are probing different parameter space. So I don't have time to talk in more detail, but there's also many other applications, such as measuring the fine structure constant, alpha, testing the weak equivalence principle, looking for effects of gravity in quantum systems. They're being proposed to measure gravitational waves at higher frequency than LIGO, also for searching dark matter, and so on and so on. So really, these are already applications in which atom interferometry is at the state of the art, right? So if we want to improve precision even more and even look for new physics and probe physics in different regimes, we need to find ways to improve precision and sensitivity, right? So what are some of the limitations of these devices? A main one is free fall time. So the measurement time that you have in your system before the atoms fly up through the system and then come back down in a fountain and splash onto the side of the vacuum chamber. And then the quantum coherence gets destroyed, of course. So to get more coherence time, people have been building taller and taller devices. So there's two examples of 10-meter towers. So these are 10-meter vacuum chambers that are magnetically shielded, very impressive systems, and, very precise. It's very expensive and very challenging engineering, right? So it gets hard. There's been other ideas to do experiments in microgravity. So you can put the atom interferometer in a zero-G plane, in a drop tower, on a sounding rocket. And actually, recently, there's been atom interferometry done on the International Space Station as part of the NASA Cold Atom Lab. And all of these devices are trying to extend the measurement time, right? And not be limited by the fact that we're on Earth and things fall. But despite all of those efforts, really, the atom fountains have been limited to a measurement time of a few seconds. And it's very challenging to reach better than that without very, very fancy engineering, I think. So this is where our approach comes in. So we take a different approach here. So our interferometer uses an optical lattice to hold the atoms. So we start with a cold sample of cesium atoms that are spin polarized. This is a plot of trajectories z as a function of time. So there's cesium atoms in a single quantum state. We send them upwards into a launch sequence against gravity. So as they're going up, we shine a pair of two beam splitter pulses. The first one splits the atom into two wave packets, one along the original trajectory and one moving upwards with the momentum kick from the photon. There's a second beam splitter that creates four arms in which there's two pairs of the same internal state and the same momentum. We use a blowaway beam, we use a push beam to get rid of one of these pairs. and just end up with two arms of the interferometer that are in the same quantum state, but now separated by this distance delta z, which is just given by the recoil of this beam-spherical repulse times the time between the pulses t. Okay, so this is where things are kind of different. So instead of letting them fall, we turn on an optical lattice, and the optical lattice loads each one of these wave packets into a different lattice site at a different height. So then the dipole force is holding each one of these wave packets individually. That happens for time tau. Hopefully tau is very long, right? Because the phase accumulated in the interferometer, this propagation phase, I was telling you how to calculate this a couple of slides ago, is integrating the Lagrangian. Okay, you end up with something like mg delta z, so the difference in potential energy difference divided by h bar times tau. So if tau is long, hopefully delta z is large, I end up with a large phase and very good sensitivity for this measurement. So that's how it works. And now we have to recombine the two arms and measure interference. So we do that with two other pi half pulses on the way down. These are also separated by time t. And we measure interference. We can plot this asymmetry as a function of whole time. And we see very nice sinusoidal fringes. So that's very nice. This is a separation of about 4 microns, 3.9 microns. So how does the experiment look like in practice? Well, this is how it used to look like. It's now taken apart, so it's not really operational. There's a next generation that's being built. But it's a pretty small setup, 1 meter tall, typical for atom interferometry and even atomic physics experiments. There's many laser beams that go inside the vacuum chamber. The atoms are in there. If you look inside, this is how it looks like, many laser beams. There's a camera that measures fluorescence from these atoms. Something that's special about this interferometer is that there's a cavity. So there's an optical cavity that takes this laser beam and creates a standing wave. So this is our optical lattice. And we think that the cavity is important because it filters out imperfections in the optical beam. So having this really pristine, spatially uniform, coherent, very well controlled optical lattice, we think is very important for preserving coherence of the quantum state. I'll talk more about that in a minute. So how well does it work? So this was kind of our first attempt in 2019. And we're already pretty excited. You already have maximum contrast, 50%. At short hold times, it kind of holds on up to 1 second. So that's already half the time that the free-fall interferometers can do. Now, even at 5 seconds, now that you're surpassing the free-fall interferometers, you still have good contrast. It's starting to go down, so there's a bit of loss in coherence. But we can measure interference after 10 seconds, 15 seconds, and even 20 seconds. So this was very, very exciting. It's already surpassing the free-fall atom interferometers. But we didn't understand this behavior. We didn't understand why the contrast decay. We didn't understand what losses coherence, and we had to really dig deep and really get to the bottom of it to really take advantage of the system. So this was a lot of the work in my postdoc, really trying to investigate the coherence mechanisms in the optical lattice. So what do we know? Well, we know empirically that the contrast decays exponentially with the whole time. So that's very nice. We quickly learned that this exponential decay time constant is not really a constant. It's actually proportional to the trap depth and the separation between the two wave packets, delta z. And now there's this thing kappa. So now that was a constant for a long time, right? It has this strange value. No one knows why. And this suggests that there's some kind of spatial variation in the lattice potential because it depends on the trap depth and delta z. But we didn't understand the reason or the exact physical mechanism that's causing that. So for a while, we really were looking through all kinds of effects that might be explained by by this empirical scaling. So part of that is building a model of your interferometer, and you can start with the simplest model that you can think about. So you have the atomic state, and then you use the beam-spherical pulse to create two wave packets. Each wave packet gets loaded into a different shelf, like a different mode of the optical lattice. It gets unloaded and then recombined. And in theory, you should get this very simple behavior of the phase in which it's just a difference in the potential energy difference between the two sides of the optical lattice. Okay, but we kind of suspect that there's something in there that we're not accounting for that has something to do with the spatial variation in the lattice potential. Okay, but what is that? Now you can go through many different models, and we did so. So these are the number of parameters and associated models that we tested over a period of almost 2 years, which we're trying to understand exactly what's causing this kappa to be the value it's at. And all of these tests were null. So, none of these models, none of this explanation, none of these possible effects really made sense. None of them are changing the decay of contrast, right? So, it's kind of a bit depressing. Like, what do you do now? Well, you keep going, right? You keep testing things until you find something that makes sense. So that's what we did. And eventually, we did find 2 parameters that does change kappa. So one of them is the transfer sample temperature. So we see a dependence of kappa with the temperature of the atomic sample in the transverse direction, so not in the vertical direction, just in the horizontal direction. And this is a inverse dependence. It's kind of shown there. This is a plot of our atoms being loaded in a cavity mode. And it's kind of a nice sloshing behavior, oscillatory that you see here. The other parameter that seemed to change the contrast decay was this amplitude of tilting. So if the experiment is tilting, it's moving left and right at some high frequency, that seemed to also affect the contrast decay and make it worse. So we can now go back to our model and try to introduce these parameters and see how they affect the coherence of the atom interferometer. And that's what we do. So this is the same. The atom is being split into 2 wave packets. But now there's some tilting in the experiment. So the bottom side of the lattice is moving a bit because of this tilt with respect to the top side. So when the atom gets loaded into the lattice, the top wave packet follows the original trajectory, but the bottom wave packet is now slightly different. There's a slight offset in that trajectory. First of all, that causes a difference in the propagation phase in the lattice because this is a different intensity of the trap potential. And then after unloading from the lattice and recombination, you also end up with the second contribution to the phase, which there's supposed to be a graph here, but it's basically from the fact that the 2 wave packets don't overlap at the end of the interferometer. So that's called the separation phase. So with this model, now we can predict what would happen in our system. And if you have a sample of many atoms, they each follow a slightly different trajectory. Each has a slightly different phase. So as time passes, there's a phase dispersion effect that increases the phase distribution in your system and reduces contrast. So we got pretty good agreement between this model and the data. And this is all written in this paper that came out last year in Nature Physics. And the question is, what can we do next? Now we know that we can improve parameters in our system to make this better. So we can get more atoms, so we can see contrast at a longer time. We can get better coherence by reducing the temperature of our atoms. And also we can reduce the intensity or measurement noise by doing all of those things. And if we can do all of that, now our model tells us what will happen, right? So initially, it seemed like the contrast was decaying exponentially up to 20 seconds. But now the model says that, well, there's going to be some cold atoms at the bottom of your trap that still preserve coherence for a longer time. So if you can just get the signal to noise in the experiment to a level that's good enough to see this behavior, you should be able to see it, right? So, okay, so let's go and see if that happens. This was where we were in 2019, right? Up to 20 seconds. Can we go beyond that? So we tried to go and take fringes at 30 seconds, and we still see coherence, at 60 seconds, and we still see coherence, and even at 70 seconds. So this is really, I think, pretty amazing. I mean, it's the longest ever spatial superposition state. It's more than 20 times longer than what's been done with atom fountains. It's really kind of bringing the quantum to the macro scale, right? I mean, we have a coffee machine upstairs. It takes 40 seconds to make a coffee. I can push the button, start my quantum superposition state. The coffee will be done, and the quantum state is still alive, right? So it's really, really cool that this is possible now to take this state that typically lives for microseconds or even shorter than that and bring it into the kind of human scale of many seconds. So I would like to tell you next about this measurement that we were doing of free forces and dark energy. But let's see if there's any questions to this section. There's one there.
Why is the error in your measurements increasing as the time increases?
Very good question. Yeah. So something that I didn't talk about too much is that you're fighting actually two effects. One of them is the loss in contrast, the coherence, but the other one is loss in atoms. So as time goes on, the atoms find their way out of the trap and they get lost, and you don't measure them in the end of the interferometer. So out here we have about 10 to 50 times less atoms than at the beginning. So then the uncertainty in each data point is much larger. Good question.
Yeah, so I was expecting that any source of noise would cause decoherence, but you mentioned that the temperature in the transverse direction only affects the decoherence time scale. So why is that? Why only in the transverse direction? Is there an explanation for that?
Yeah, so the explanation is this motion of the atoms inside the traps. So then if you have a higher temperature, there's going to be more motion, and that will create more decoherence. Why not in the longitudinal? Or yeah, so I mean, intuitively, I think the longitudinal temperature might matter less. I think because it's common mode to the interferometer. So yeah.
Would matter less, but in the transverse, the average momentum is zero, basically. So that's
yeah. I mean, there's still a lot we're understanding about the system, but that's at least my intuition. That's the case. Great.
But the principle, if you could preserve this coherence for longer and longer times, maybe this effect of the longitudinal temperature
Yeah. So at some point, everything will matter. Yeah, and I think, I don't know if Brian is somewhere here, he had an idea of, when you load the two wave back inside the lattice, if you do that a bit differentially, you will get the phase shift from that. So a lot of things will start to matter as you increase sensitivity. There's a question like there.
How does your uncertainty of your measurement scale with the number of atoms? Like what type of power do you get?
Yeah, so in these experiments, the atoms are independent of each other. So you get the usual, standard quantum limit scaling of square root of n. Yeah. But one of the directions that we're interested in is to, look at entanglement and sort of using interactions in the ensemble to push beyond that and get closer to a Heisenberg scaling of 1 over n or something like that. It's quite challenging so far. Okay, let's keep going. Kind of running out of time. Okay, so we have really good coherence. What can we do with it? We want to use this in a real physics measurement. We want to show that this can do some kind of precision measurement with better than anything else, right? So what we set to do is to measure the gravity pull from the small tungsten source mass. It's about 1 inch in length and diameter. We hold the atoms close to the tungsten source mass and measure the gravity from the Earth, right? That's the largest component. And then there's a small component from the gravity of this tungsten source mass. We expect the signal to be quite small, so 35 nanometers per second squared. That's 3 parts per billion of Earth's gravity. So you expect this measurement will be hard. How can we do that? Well, first you have to increase the precision or the signal-to-noise ratio in this measurement. And using this increased coherence, we were able to do that. Now we need techniques to be able to move the atoms close to the source mass and use that as a way to reduce systematics. So we have an atom elevator that you can show allows us to move the atoms at different locations about the cavity mode. But that's not enough, right? You have to start looking at systematics and drifts and noise and so on. And these are some sources of systematic noise and drift that might occur. Right, some of them make a lot of sense. There's field gradients, there's strong interaction with the lattice, there's tides. Some of them are funny. There's maybe a magnet next door that someone turns on, or maybe someone walks by and now the gravitational field change. So, there's things to keep in mind. So how do we address this? We use a trick that I learned in my PhD in ACME, which is differential measurement. So if you can turn on and off the signal of interest, you can isolate it from all of the other sources of noise. And that's what we do here. So we move the source mass in. That's this M parameter +1. And then we move it out, M0. And then we also move the atoms below the source mass, E -1, or above the source mass, E +1. So we effectively, I don't know what's happening there, but we do 4 measurements in which the source mass is nearby and far away, and the atoms are above and below, and then we alternate between the two on fast time scales, 45 seconds for this position switch and 20 minutes for the mass position. So at the end, we have 4 measurements, and now choosing the right linear combination of these 4 measurements allows us to extract the acceleration from the source mass and isolate all of the other systematic effects that might be occurring in the system. So let's see how well that works. So we took data for about 2 months, 45 days, 400 hours. And if you look at the uncorrelated component of this data set, it's a mess. I mean, look at that. The acceleration is jumping around by factors of by 1,000 nanometers per second squared. Remember, we're trying to measure at a few nanometers per second squared precision. So is there any hope, right? I mean, this is terrible. Okay, but if we look at the correlated component, right, this carefully chosen linear combination, that looks much cleaner, right? That's a really nice data set with very small spread. And if you zoom in, it looks actually very nice. And the distribution of the error bars matches what you would expect from the spread of the data points. And you can even plot this distribution of this time series, and it follows a very nice Gaussian profile. So all of the noise that was in this non-correlated component kind of got taken away by this fast switches that we were doing. So it's a very, very powerful method to really reduce noise and systematics. How do we look for systematics in this experiment? We have very different parameters, and this is only a few of them. There's really over 40 parameters. We found a few systematics. Some of them we knew and we were expecting. Some of them were new and we had to understand, but they were sort of easy to understand. Some of them are just limits on possible effects that we did not really observe, but we put them in just in case to be very conservative. This is all described in a paper that we put out last year. What's important here at the end is that the total uncertainty, so the combined systematic and statistical uncertainty, is this number 6 nanometers per second. And this is 5 times better than any previous measurements. And all of these previous measurements use atoms in free fall. So we do our measurement blind. So that means that we add a random number to the result, and we keep that there until the entire data set it's acquired, all of the analysis is done. So we don't bias ourselves to one result or the other. Maybe you like Newton and you think Newtonian gravity is right. Maybe you don't. It doesn't matter. We don't know what the result is until the end. So then we have like a little ceremony, like a little meeting in which, it's a bit stressful because you don't know what you're going to find. Is this going to be new physics? Is this going to be a huge systematic that you forgot about, right? It's probably more likely the second alternative. Yeah, then we take a look at the number, and this is what we found. The acceleration from the source mass was 33.3, plus minus 5.6 statistical, plus minus 2.7 systematic nanometers per second squared. We can compare that with what Newton thinks it should be. That was 35.2 plus minus 1 nanometers per second squared. They completely agree with each other, and we can use that to put a limit on the deviation of our measurement from the expected Newtonian gravity to below 13 nanometers per second squared with 95% confidence, right? So that's great. What does this tell us about new physics, about field forces, about these chameleons, dark energy? We can now go back to our exclusion plot of this chameleon theories, and we can put a new band, and this is this orange band. So you can see that our bounds are now better than the previous bounds by a factor of about 5. And more importantly, is kind of illuminating this horizontal black line, which is kind of the preferred value of this interaction parameter given the existing dark energy density in the universe. So we kind of excluded this theory in this sort of form, right? Of course, you can always change different forms. There's ways to improve this. But this is really exciting because it's the first time we used the lattice atom interferometer in a measurement. And we were able to get a precision of 6 times better than any previous results and illuminate the parameter space of a real physical theory. So this is all described in this paper. I can more details there. And I'll take a short break now and then tell you about what we want to do here at Arizona. I have a few minutes. Yeah.
So in the lattice interferometer, why is it important to put both arms of the interferometer in the same momentum state before you reason the lattice?
Oh yeah, so that's that's a good question. So the reason is because then both wave packets can load in the same lattice at the same time, you know. So they're both reaching the apex of the trajectory at the same time, and then you turn on the lattice, and each arm gets loaded into a separate lattice site, but with the same velocity, with the same momentum. Yeah.
Tungsten source is not electrically charged.
That's a good question. So the atoms are pretty far away. This measurement is about, I think a few millimeters. The tungsten format is grounded to the chamber. Yeah, that's.
Why do they use tungsten?
So tungsten has a very high density. It's easy to machine. Those are the main reasons. The uniformity is not as good. So, if you wanted to do a big G measurement, there's better choices, I think. But yeah, it's pretty available, it's pretty non-toxic, yeah, affordable, easy to machine. Okay, so in the interest of time, I'll keep going. So let me tell you about our work here. So I got at Arizona in Tucson in December. These are some of the events we've had since then. So we went to Home Depot and tried to get some surprise, and they kept falling out of the car. So we had to stop on the side of the road. Almost got killed by cars passing by. This is Ken. He's right here. He is testing his electromagnetic calibration on the top of a trash can. It used to be on the table, but then we realized that the table is magnetic, so it's actually affecting the measurement. So we just put it on the trash can. It's far away from any magnetic sources. We found this really fun mirror here. We took some pictures. So we have a really good group here. We're having a lot of fun together. Paul and Andre are second and first year grad students. Ken is here as a lab tech, and we have a couple of undergrads joining us recently. So it's been a lot of fun being here, and thank you all for welcoming me. It's been great so far. We're also busy in labs, so we're not only having fun, we're also doing science. So these are some of the projects that we've been working on. So this is a technical kind of upgrade. So we're building this electromagnet that can go inside the vacuum chamber. These things, used to be water cooled or, cryogen cooled before. That's a lot of work. So we're trying to see if we can use heat pipes to get the heat out of the vacuum chamber instead in a passive system. This is a picture of the lab from yesterday. So it's the vacuum chamber in which the atoms will go in soon. So it's kind of getting ready. We're planning to pump down hopefully next week. There's no delays with suppliers. And we also have laser systems that are coming online. This is a spectroscopy signal we got a couple of weeks ago of cesium atoms inside our spectroscopy cell. And the lasers are starting to get set up too. And the idea is to get these atoms in the vacuum chamber soon and start to do quantum science, right? So very excited for that. There's two main directions, I think, to the research that we plan to do here. One of them is to build a next generation atom interferometer based on the lattice technique that will be used for fundamental physics. And then one of them is to build a compact device, a portable, simpler system that can be used for atom interferometry and gravimetry in the field. So you bring this technology out into the real world. So for this system, this is a diagram of what we're planning to do, and it's already under construction. So there's three main upgrades that we are working on. I already mentioned this in-vacuum coil that we'll use to apply the magnetic field and gradients that we need to implement evaporative cooling. So this is to reduce the atom temperature even more. And this is one of the factors that should improve coherence, if you remember from the model a few slides back. Then we have a monolithic optical cavity. So it's a glass spacer that the mirrors get mounted to. And that should provide a lot more stability and lower vibrations. Again, vibrations do affect coherence, so reducing that will be quite important for the performance. And we also have plans to try different source mass configurations. There's a few different applications here. One of them is to measure G, the gravitational constant. But then we also plan to use these configurations to probe non-Newtonian gravities, chameleons, screen potentials, look at deviations from the inverse square law, and maybe even look at quantum sort of gravity effects in our quantum system. Should be careful what I say there. So how is this going to work, right? So if you're not convinced of my PowerPoint skills, this is my last chance, I think. So okay, we'll have a magneto-optical trap with about 1 billion atoms at about 1 microkelvin, maybe a couple of microkelvin temperature. Okay, we do 3 stages of cooling and then quantum state preparation to bring them all into the same quantum state in a very low temperature of about 1 nanokelvin, hopefully, or so. You can see they're smaller. We launch the atoms and use beam splitters to bring them close to the source mass. So there's a beam splitter that now makes each atom go from a location into a superposition of 2 wave packets at different heights. We should have about 1 million atoms for our measurements. We turn on our optical lattice, and the atoms get loaded inside the optical lattice. They accumulate this phase, again, just the difference in the potential energy between the 2 arms. That's hopefully long, so there's 60 seconds, but maybe this is not seconds, maybe this is minutes, right? 60 minutes or hours, 12 hours, no, that'll be crazy. So hopefully we do a good job, and this measurement time can be quite long, so we get a lot of sensitivity. Turn off the optical lattice, recombine the 2 arms, and then measure the interference at the end, right? So very nice. We think that the systematics for measuring big G could be reduced. So this is a list of systematics from the previous atom interferometry result. A lot of the systematics have to do with imperfections in the system, such as the atom positioning accuracy, properties of the source mass, and imaging. And we think that the optical lattice can address each one of these problems by holding the atoms in very precise locations in the optical lattice. Use a smaller source mass, and then the detection region should be much smaller. So it should be much easier to characterize some of these effects. So we think that we should be able to reduce systematics to below 10 parts per million. So in a first measurement using cesium, we think that we can sort of do better than the previous atom interferometry result and be competitive with the other classical sensors in this sort of measurement, right? So we have ideas for what to do next too. So you can replace cesium and instead use strontium. Strontium is a nice atom because it has 2 valence electrons. So that means that along with this singular structure that you usually have in cesium, which is an alkali, you also have this triplet structure from the 2 electrons. And between the 2, you have this very narrow clock transitions that can be a really nice resource for your quantum experiments, so improve coherence. So we think that we can get to lower temperatures sort of with easy mod cooling, less collisions, so there's not going to be the coherence. We can use Kroc states in our experiments, and there's even fermionic and bosonic isotopes, so you can look at interactions and maybe using that as a resource to create entanglement, squeezing, and reduce systematics that way. So with that, we hope that we can get even better precision, so sort of really go beyond the state of the art and really be kind of at the cutting edge of this type of measurements. Strontium also has this Kroc states, which give you other opportunities, I think. So one of the things that we could do is to measure the atomic mass defect of the strontium atom being in the ground state and the excited Kroc state. So if you measure a phase difference, it's basically measuring the weight of the atom, from this one photon that's connecting the 2 states. So that would be a very, really precise weight balance. You're measuring the weight of this atom to 10 to the minus 33 grams for a level of accuracy. So that would be a nice demonstration, but you can also do fundamental physics with that. So you can imagine that instead of having each arm of the interferometer in a single internal state, you can have it in a superposition of Kroc states. And now each one of these arms is in a different gravitational potential. So the different Krocs will have different gravitational redshift. And because of that, you expect that there's a bit of leaking of which way information out of your system through the gravitational redshift. So this is a fundamental question in physics. Can gravity property, the redshift, provide which way information in a quantum interferometer? So this is sort of question that we might be able to answer. So if you see a decay and revival of your contrast at the frequency of this Kroc, then that would be a signature of that. So we are building one apparatus, but we hope to have many different results. There's also some other ideas of using this sort of device to measure atom recoil and even look into the fine structure constant. But I also wanted to tell you about the second direction, which is mobile atom gravimetry. So the question is, how do you bring quantum sensor in industrial and commercial space? And I think there's a few challenges. You have to find applications. I think the applications here are clear, right? Measuring gravity, studying geophysics, learn about the rock structure underneath are sort of obvious applications for this sort of device. Make it more robust. That's one of the challenges. So that would be interesting for inertial navigation, maybe in demanding conditions on the board of a plane or on ships at sea. And the other question is, how do you integrate this probably with other sensors and make it useful in a commercial application? So you can imagine hybrid classical and quantum sensors in which the classical sensor is really good at short time, and maybe the quantum sensor has very long term accuracy. So some of the challenges of this sort of device is atom interferometers on mobile platforms with atoms in free fall are this. So there's a lot of sensitivity to vibrations. They're sensitive to vertical alignment and also magnetic fields. And we have identified that the lattice interferometer can address these issues. So this is all described in this paper. So first of all, the lattice interferometer holds the atoms for the entire measurement time. So that means that the vibrations of the setup get averaged out instead of aliased. The interferometer has a trapping potential in the horizontal direction, so the atoms don't spill out. So you can measure with the tilt of the experiment. And also it's quite less sensitive to magnetic fields. First, because it's in a very small volume, and there's also ways to cancel out environmental magnetic fields. So we think that it would be really cool to try to build a compact device that we can run first in the lab, but then also bring it out for demonstrations, allow access of the public to this quantum science. We imagine a small, meter cube or something, single vacuum chamber setup. We would need to set up a simplified laser setup. I think being here is great because there's a lot of experience with integrated photonics, right? On-chip atomic sources and so on. So I think that's something I'm looking forward to collaborate on. We want to put this on a mobile platform, transportable, bring it out, maybe collaborate with everyone here to make that happen. And these are some of the results that we're kind of hoping to achieve here. So this is my summary slide. So I told you about how to do atom interferometry, but in a different way. In this case, the atoms are trapped in an optical lattice, so they're not falling like before. I show you how we can use that to achieve the longest ever spatial superposition state, which now has coherence at the minute scale. So that's again more than an order of magnitude longer than what's been done previously. I showed you how we use that in a first precision measurement, so in a first measurement of fundamental physics by probing parameter space that was not accessed before for this series of screen potentials, chameleon symmetrons that try to explain dark energy. And some of the directions and ideas that we're setting up right now downstairs, right here, to start to test new physics and also bring this technology out into the real world. Thank you. There are questions? In the back.
Ask an outsider question. Now look at my phone, it bothers me because it always turns in the wrong way. Can you say a few words about
contrasting this technology, how good you think it can get? I mean, I assume I don't have an atom interferometer.
No, you don't. No, you don't. Yeah.
So how?
So the ones that I'm showing on the first slide are about, this big right now, and a few £100, and they cost about $1 million or so. So they're not in the phones yet, but that's one of the questions, right? Of course, the phone, like in our phones, if you have a smartphone, you'll have about 15 sensors or something, and one of them is an inertial sensor, an accelerometer, and it's a classical device, right? And the question is, can you take an atomic system and put it there? And I can give the example of atomic clocks. There are atomic clocks on chips now available. They're not quite, at the level at which they're in smartphones, but they're close to that. So I think following in that technology, I think atom interferometry and inertial sensors could get there at some time, but we're far from that. Yeah. So that's why I think the university and academic environment is where a lot of this has to come from, because the commercial applications are still a few years down the line. Yeah. And the advantage of atomic systems is, again, sort of this really simplicity, right? If you can take this atomic system and put it in a single quantum state, now you understand its behavior really well. But the challenge of that is having the infrastructure and the technology to be able to do that, and miniaturizing that and putting it into a small package is I think, a lot of the work to be done. Mm-hmm. But if you do that, then the long-term accuracy can be much better, right? You're not limited by changes in your classical sensor, like, deposition of metals, temperature, and so on. And the long-term accuracy can be quite good. Mm-hmm.
The fundamental, might be a little more fundamental question. When you increase the precision of your measurement, why does it expand the boundary of the exclusion in this?
So this one. What we are doing, we're measuring the acceleration from the tungsten source mass. And so you can think of this chameleon field of an additional force, a fifth force, that comes from the fact that there is, it's kind of like ether. You can think about it that way, right? There's an additional field that we don't know about. So now, if I look at that field, right, it will be quite weak where the source mass is, because the local matter energy density is high. And then as I go into the vacuum chamber, it gets very strong because the local matter density is high. So there's going to be a gradient in that potential, and that gradient will create a new force, a fifth force. And that's what the atom interferometer is measuring. It's looking for deviations from the expected Newtonian gravity. We know that's there, but is there something else? Is there an anomaly? Is there a fifth force that's causing an additional effect? And if not, then I can put bounds on the parameters of this fifth force. So I know that the strength must be lower than some value that's coming from the measured acceleration. Hopefully that's, I don't know if that was. Yeah, so there's actually more than two, but I am only showing two on this plot. So one of them is the interaction strength, and the other one is the mass of this new particle. But there's also a scaling law that you can assume. So, in this sort of scaling, in which I think they assume a power law with power of 1 or something like that, this is fully kind of excluded now, at least at the level of dark energy that you would expect. But you can assume a different scaling law, and then you're still probing that parameter space. Mm-hmm.
Cris.
Justin.
I was wondering, are there any resolution effects of the laser trapping atoms at discrete locations?
Resolution effects, what do you mean by that?
So you send your atoms up, and then the optical lattice will have particular discrete locations where the atoms will get right? Mm-hmm. Is there, so say that one atom might be approaching a particular location, but it's between two locations where it could get trapped. And Would there be any effects because?
Yeah, so that's similar, I think, to what Brian was talking about, right? Just like loading of the atoms inside the lattice. If you're not exactly matched to the lattice spacing, what happens? And I'm not sure. I mean, I think if both wave packets are at the same offset, probably they both get the same phase in that process. So we have done that before. Yeah, so you can set it so that it's exactly in the middle. So actually it's very fun. You know, what happens is that one of the wave packets gets split again by the lattice into two additional wave packets. And now you have an interferometer with 3 arms. And now you can interfere this two, and you can interfere this two, and you get both frequencies. And then you get the bit node between the two frequencies, right? Just like you would expect. So you can use the lattice as a kind of beam splitter.
And then those two, since they're closer, they'll experience less decoherence.
The two, which two?
So you said that if it's going to like the middle of the position, it'll split into two.
Yeah.
And then these two will experience less decoherence.
That's true. We actually can measure those experimentally because what happens is the wave packet size, the de Broglie wavelength of the atom, is almost the separation of the lattice. So if you measure adjacent sides, they're still overlapped. So you're doing a Ramsey interferometer. You're measuring the internal state of the atom instead of the spatial superposition state. So yeah, we're not quite sure, but maybe, yeah, could be.
All right. In the interest of time, let's thank the speaker.